Hi everyone, welcome back to Spratt STEM Academy. In today's video, we're going to be talking about the ideal gas law. We're going to talk about the ideal gas law formula, and then we're going to do two examples that go over how to use it in the real world. But before I go into the formula, I want to talk about the ideal gas theory. The ideal gas theory is just going to kind of explain what an ideal gas is. And this is going to be really important to know for chemistry because oftentimes we want to deal with something that is ideal or something that is kind of most preferred in a way. But essentially, an ideal gas is a gas where the atoms do not exert forces on each other, but they do collide with the walls of the container that they're in elastic collisions. So the ideal gas theory is pretty complex, but essentially you want to know that it's going to be used as a good approximation of the behavior of an ideal gas. So just kind of keep that in mind before we get into the calculations. I like to go over it because instead of just going straight into the math and plugging in numbers, I think it's really important to know why you're using the formula and what exactly it can be used for. But now that we've gone over that, let's talk about the ideal gas law, which states PV equals nRT. And I'm going to talk about what all of these different letters mean. So this P is going to be pressure. So the P stands for pressure. And it's going to be pressure. And the unit for pressure that we're going to most commonly use for the ideal gas law is going to be atmospheres. So I'm going to write atmospheres. So that's just ATM. This V right here, that stands for volume. And in ideal gas law, we're often referring to volume in liters. This N is referring to the number of moles. So I'm just going to leave that as moles. And then R, this is going to be a constant. Okay, this is a constant, which means that's a number that's always going to stay the same no matter what. So that's not something you have to solve for. And all it is it's going to be 0.08206. And the unit is going to be liters times atmospheres divided by moles times Kelvin. So that's the R constant in the ideal gas law, 0.08206. And then lastly, we have T, which stands for temperature. And the unit for temperature is going to be Kelvin, which is K. And sometimes, before we go into our problems, sometimes a problem will give you your temperature in Celsius. To get from Celsius to Kelvin, all you have to do is take your Celsius temperature and add 273.15. That is going to take you to Kelvin. So that is the ideal gas law formula and what each variable means. Now let's go into some problems. Our first problem is, at what temperature will 0.654 moles of neon gas occupy 12.30 liters of 1.95 atmospheres? So we have our problem here. Let's write down our ideal gas law formula. PV equals nRT. Now, looking back at the problem, let's figure out what exactly it is that we're looking for. We want to know at what temperature. So we know we're going to be solving for temperature, which is T. So let's isolate T to get it by itself so that we can find it easily. So I'm going to take T, and in order to get T by itself, all we have to do is divide each side by N and R. So moles in the gas constant, R. So we're going to be left with T equals PV over NR. So that is going to be our formula. And it's the same formula, we've just manipulated it to make it easier on ourselves. So let's now plug in our information. We have moles, we have volume, and we have pressure. So this would be P, volume is V, and then moles is N. So now let's plug everything in. T equals our pressure, which is 1.95 atoms. And make sure to write your units. It's going to help you when you're trying to find your final calculation. That's going to be multiplied by volume, which is 12.30 liters, over. And then on the bottom, we have the number of moles, 0.654 moles times R, the gas constant, 0.08206. Liters times atmospheres over moles times Kelvin. So that's all 1 unit for the gas constant. Okay, now before we put this into our calculator, because we are not going to do this in our head, I want you guys to see the units and how they work out. We know that we're looking for temperature, so our final unit should be K. So meaning we should only be left with K. So can we cross out some units? We can, in fact, do that. Let's start on the bottom. Here we have moles here and moles on the bottom here. So those do, in fact, cancel out. We know that up here we have liters times atmospheres. We also have that down here. So those will also cancel out. And then we're only left with this K. So we know that we've manipulated our equation correctly because we're left with Kelvin, which is going to give us our temperature. So if we plug this all in, we are going to end up with our temperature being 446.92 Kelvin. And so that is going to be the temperature at which the gas, or 0.654 moles of neon gas, will occupy 12.30 liters at 1.95 atmospheres. And so that is how we do this question. Now for this question, we have a lot of information, but let's read and figure out what we know. A cylinder of oxygen, O2, used in breathing by emphysema patients has a volume of 3.00 liters at a pressure of 10 atmospheres. If the pressure of the cylinder is 28.0 degrees Celsius, how many moles of oxygen is in the cylinder? So, let's look at what we know. We know that we have a volume, we have a pressure, and we even have a temperature. What we're looking for then is moles of oxygen. We're going to be looking for N. Let's write down our formula. PV equals nRT. And we know we're looking for N, that's our missing number. So let's manipulate this to get N by itself. So to get N by itself, we're going to put N, and we're just going to divide the RT on both sides. So that'll give us PV over RT. And that's how we're going to solve for moles of oxygen. So let's write down N equals. We have our pressure, and it's already in the correct unit, so we can go on ahead and write 10.0 atmospheres. It's going to be multiplied by the volume, which they told us is 3 liters. That's also in a correct unit. It's going to be over R, which is our constant, so nothing to change there. So 0.08206 liters times atmospheres over moles times Kelvin. And then lastly, our temperature, which is 28.0 degrees Celsius. But we simply cannot write this in because our units wouldn't cancel out to give us moles. So we know we need this to be in Kelvin. So how do we get from 28.0 degrees Celsius to Kelvin? Refer back to what I told you at the beginning of this video. In order to get from Celsius to Kelvin, you need to add 273.15. So 28 plus 273.15, that's going to give you 301.15 Kelvin. And so 28 degrees Celsius is 301.15 Kelvin. So let's now write that in. And now, if we look, let's make sure everything cancels out. Liters and atmospheres do cancel out. Kelvin cancels out. So we're only left with moles, which is exactly what we're looking for. So now, if we plug this in to our calculator, we get 10 times 3 on the top, 0.08206 times 301.15 on the bottom, and we are left with 1.21 moles of oxygen. And that is a solution to this problem. So We've covered ideal gas law, and we've used it to solve some real-world problems. I hope this all made sense, and I hope you enjoyed. Make sure you give this video a like. Don't forget to comment and subscribe. Thank you for watching.